Okay, let's introduce you to redox reactions, which are a combination of oxidation and reduction reactions. And kind of depending on the context of what you're learning them in, they're going to take on kind of different roles in various biological functions and various chemical functions. There's a lot of different examples of redox reactions, and kind of how you learn about them depends on the context in which you're going to be studying them. So I'm kind of pitching this at sort of an introductory chemistry level. So I want to do some kind of definition of terms and kind of process for how we handle redox reactions. So oxidation, by definition here, is any chemical process where electrons are lost. And in a biological context, which I just have here as kind of a side note, because if you're studying biology classes or if you're going on into biological sciences, they tend to think about it in a slightly different way, because biomolecules, it's all about kind of the movement of hydrogens and oxygen. So an oxidation reaction is any reaction where hydrogen atoms are lost or oxygen atoms are gained. Now, reduction is any chemical process or any chemical reaction where electrons are gained. And again, in a biological standpoint, this would be where hydrogen atoms are gained or oxygen atoms are lost. So essentially, they're the exact opposite of each other, and one feeds into the other. Now, because it's kind of a weird thing for reduction to mean a gain in something, there's a couple important mnemonic devices that we as chemists use to remember this. And the first one is oil rig, which we'll just put here right at the top. Oil rig, where oxidation is loss of electrons and reduction is gaining electrons. The other handy mnemonic, if you don't like oil rig, is Leo the lion goes grrr. So that would be the loss of electrons is oxidation, the gain of electrons is reduction. So whichever one works better for you in terms of a memorization device, oxidation is loss of electrons, reduction is gain. And again, from a standpoint of the chemist is interested in the movement of electrons in a chemical process, so that's kind of where our focus is. Let's talk about some applications of this. One of the main applications is in the formation of ionic compounds, because we're talking about gaining and losing electrons. So let's think about the formation of calcium fluoride here. What is actually happening? Calcium is going from neutral calcium to calcium in an ionic compound. So calcium is going from calcium to calcium 2+. And I know that it's a 2+ charge because of where it is on the periodic table. It's in the alkaline earth metal column. And my fluorine here is going from fluorine that's diatomic in its elemental form to 2 fluoride ions. And we know that fluorine has a -1 charge because it's in our halogen column. So what's really happening between these two steps? Well, calcium, to go to calcium 2+, needs to lose electrons. I need to lose 2 electrons, and I can show the loss of those 2 electrons by putting them as products. So electrons on the product side of my reaction indicate that they are being lost. So this is kind of my oxidation step. And then these electrons have to go somewhere. They're going to get picked up by this fluorine, because my fluorine is getting more negative. So I could think about this as a gain of electrons here on my reactant side, which indicates reduction. And again, the terminology here is infuriating for many students, because the reduction means that I'm getting more of something, which is kind of counterintuitive. All right, so oxidation is loss of electrons. Electrons are in the products. Reduction is gain of electrons. So I'm getting those electrons then on my reactant side. Now these little reactions that I've put here show the movement of electrons, the transfer of electrons here. These are called half reactions. And these half reactions show the electrons being lost and the electrons being gained, which again for chemists are really the interesting part about all of this. Now, just some more annoying terminology for you, because the vocab in oxidation reduction processes is quite challenging. So whatever is being oxidized, which in this case is my calcium, because it's losing electrons, is called, and you're going to hate this, the reducing agent. An agent means someone who's making something happen. So what they're making happen is reduction by losing those electrons. So using that same logic, what do you think we call the fluorine? Well, hopefully you're thinking, well, this is nice and counterintuitive. This is called my oxidizing agent, because it's allowing for the loss of electrons to occur. So whatever's being oxidized is the reducing agent, whatever's being reduced is the oxidizing agent. Now, if we want to figure out whether or not redox is happening in a chemical process, then we have to keep our definitions in mind. So any chemical reaction where electrons are lost, or hydrogen atoms are lost, or oxygen atoms are gained, or then reduction, anything where electrons are gained, or hydrogen atoms are gained, or oxygen atoms are lost. If we're kind of mapping out these guys in chemical processes, then we can figure out what's going on. Do we have a redox reaction? But in order to make that a little bit easier, it's good to look at what is called the oxidation state, or the oxidation numbers. And there's some particular rules that we have. Here's my rules for assigning oxidation numbers. So an oxidation number is a number that shows the oxidative state of an element in a chemical process. And I can assign them to every single element in a chemical reaction. Anytime you have an element in its elemental state, that oxidation number is 0. So if I have gold atoms that are in their elemental state, then that would be a 0. If I have chlorine, gaseous chlorine that's diatomic, even though there's 2 of them, it's still the elemental form of chlorine. So that would be a 0 as well in terms of its oxidative state. If I had sulfur, which is octavalent in its elemental state, then I would have 8 atoms of sulfur and its oxidative number would be 0. Now monoatomic ions, so that would be any individual atom with a charge on it. The charge of that atom is going to be the oxidation number. So if I have something like sodium, for example, then sodium has a +1 charge. The oxidative number, or the oxidative state, is a +1 state. So pretty straightforward for monoatomic ions. The charge is the oxidation state. And that goes for negative ions too. So if I have sulfur as an ion, the sulfide ion, it's got a -2 charge, so that would give me a -2 oxidative state. Now there's 3 rules for specific elements. You've already kind of seen that oxygen and hydrogen are pretty important, especially in a biological context. So oxygen kind of has its own rule. Anytime it's in a compound, it's a -2. Hydrogen, whenever it's in a compound, is +1, except when it's not, which sometimes it's a -1. That goes a little bit beyond the scope of this particular video. And then fluorine, because of its electronegativity and the way that it does chemistry, is always a -1. So these are the rules. Let's apply them to another type of chemical process. So let's look at corrosion, which is any sort of chemical process that deteriorates metals. So think about rusting, for example, which is the reaction that I have here. If I take iron, metal, and I stick it outside, it reacts with the oxygen here, and it forms iron oxide. So if I wanted to assign oxidation numbers to this thing, iron is in its elemental form, so it's a 0. I have a colleague that says that if it's a single lady, then you're going to put a ring on it, right? A little nod to Beyonce there. Oxygen gas then is also in its elemental form, so it's a 0 as well. And now when I put it in my elemental form over here, my ionic form over here, I have a metal paired with a non-metal, so I know that this is an ionic compound. So oxygen, I have a rule about, it's -2. Iron here is going to be the charge on my iron. Well, iron is a transition metal, so it can have a number of different charges. So I need to figure out if it's iron +2 or iron +3, because that's what iron likes to be. So I need to figure out what it's paired with. Well, if I multiply up, this gives me -2 times my 3. That's a total of -6. I have to balance out a -6 with a +6, right? In order to get to a neutral compound, which we know that we are, it has to be neutral also in terms of its oxidative state. So +6 then, which is balancing out my -6, divided by the 2 gives me a +3. So I learned this as the multiply up, divide down method for figuring out the oxidation numbers for these things. And all of the oxidative states and numbers when you factor in how many there are for each of those elements, have to equal 0 in a chemical compound. So you should be able to figure out all of them for an element depending on where they're kind of located and what they're all paired with. Okay, so what the heck is happening? How do we use these oxidation numbers? Well, what I'm doing is I'm looking at how they change going from reactants to products. If there's an increase in oxidation number, that's oxidation. So that in this case is going to be my iron. So let's write that half reaction then. I'm going from 4 irons on this side to 4 irons on my product side. But my irons on my product side are in a 3+ oxidative state. And sometimes, for some people, they like to put the 0 oxidative state when the thing is neutral. And that's fine if that kind of helps show what's going on. Now, if we go back to our oxidation numbers, a decrease in oxidation number is reduction. This is where reduction actually makes sense in terms of a term, right? Because reducing something means it goes down. What's going down? My oxidation number, going from reactants to products. So I started off at the 0, now I'm at a -2. So I'm going from 3 oxygens that are in their diatomic form to 6 oxide ions, right? 2 times my 3 gives me 6 of my oxide ions, my oxygens in a 2- state. Okay, so what's happening? How many electrons are moving around in this process? Oxidation is loss. So if I take my coefficient times my charge, that's going to tell me how many electrons are lost, right? For each iron atom, I've lost 3 electrons. There's 4 iron atoms. That gives me 12 electrons lost. For my oxygen, I have 6 atoms here of oxygen total, right? 3 of my diatomic molecules, and then I get to 6 oxide. If I do coefficient times the charge, that gives me 12 electrons that I have to gain in order to get more negative here, right? Iron's getting more positive, oxygen's getting more negative, iron is being oxidized, oxygen is being reduced. And we should have the same number of electrons lost and gained on both sides of my process here, otherwise it's not balanced. All right, let's look at one more example. If we think about combustion, a combustion reaction is a reaction of a hydrocarbon. That's a molecule that's made up of just hydrogens and carbons that's reacting with oxygen in order to form carbon dioxide and water. And these processes put out a lot of energy. So a combustion reaction is used in engines, for example, to power things. That chemical energy, right, from burning a fuel like methane here is going to cause kinetic energy or mechanical energy that's going to drive a piston in your car or your lawnmower or whatever. Okay, so we have a balanced chemical process here. Instead of assigning oxidation numbers, let's think about that second definition of oxidation and reduction. So what's happening with my carbon here? Carbon is going from methane to carbon dioxide if we're mapping out my carbon here. So if I go from one side to another, I'm losing hydrogen. And loss of hydrogen, kind of in a biological context, is oxidation. And again, we could assign oxidation numbers, and I would encourage you to do so because this will help you map this out as well. Just is a little trickier with the oxidation numbers. So the loss of hydrogen gives you an oxidation process. So that means that our carbon is being oxidized. And if we look at our oxygen here, we're gaining hydrogen to form the water, which means that it's being reduced. So this is kind of how we would see this in another context. So we as chemists think about pushing around electrons and transferring electrons in order to get either more positive or more negative. Now, in these, we have molecular or covalent compounds all the way across. We're not talking about the formation of ions, so there's nothing here with set charges. So if we really look at the movement of these hydrogens and kind of what's being lost and what's being gained, then that gives us an indication of the oxidation and reduction, which is no less a redox process than the formation of my ions. Okay, so hopefully this helps to give you an introduction to some redox processes, some examples of applications, and how to assign those oxidation numbers. And if you have any questions on that, don't hesitate to reach out.